Good afternoon, everyone. My name is Juan Morel. I am a physics teacher at Jack E. Singley Academy, and today I will be presenting some research that I did last year in the 2019 to 2020 academic year. I have about 10, 15 minutes to do this, so let me go ahead and get started. All right, I'm going to go ahead and share my screen. First things first, let me introduce the program that I was involved with this research. The program is called WIPRO, and it's UNT Dallas wonderful professor Dr. Narayan, who served as our guide through this research. This was part of a science education fellowship that I did in the first year. There was mostly collaborative projects with teachers across grade levels, science teachers across grade levels, and also within our grade level across disciplines. In the second year of this program, the project was more independent. So this is the independent portion, the second year, the culmination of this WIPRO program. The project that I am involved with is called Playground Physics for Secondary Students. And I was inspired by another research fellow, the presentation that she demonstrated with her elementary students. And I said, wow, this is body kinesthetic physics in the playground for elementary. Why not do it at the high school level as well? So that was sort of my motivation. So let me go ahead and go right into the research, okay? So first and foremost, let's go into the research question and rationale. The idea was essentially to compare learning outcomes using pre-test, post-test assessment of a student's ability to calculate a law of conservation of energy word problem, okay? And the idea was the control groups, all students would receive in-class instruction in class labs, but the experimental groups of students would also be undergoing a self-paced guided inquiry activity over the Thanksgiving break. So the idea was to reinforce their prior learning by performing this self-paced activity, preparing them for university labs, which are often self-paced, and especially now with so much digital learning going on, even if you're not going to a digital or online school. And then again, learning through practical engagement is big in education nowadays. Let's look at some of the research that I used that inspired me into this particular project. So one study showing that students who perform hands-on activities, physics activities in the playground perform better than those who didn't. This was in 2017. Then in 2011 study showing that POGIL stands for process-oriented guided inquiry learning. So sort of like the self-paced teachers, the facilitator students, the active learner style of pedagogy, as opposed to the more passive student lecture-centric, teacher-centric style of dissemination of information, right? So students who engaged in this style of process-oriented learning did better on sort of compared to the traditional lecture students in a secondary chemistry setting. Another one that was really important for me was how much academic gain students lose over the summer. This especially impacts our lower income students. Myself being from a lower income working class background, I'm an immigrant, wasn't even born in the United States, so often would help my mom, wonderful lady, love her to death, strong woman, taught me everything about morals, and I love her to death. She wasn't prepared to help me academically. And so a lot of these students are losing their academic gains over the summer as a result of the fact that their parents are not prepared to really push them academically even while they're away from school. So this study was, there's a lot more that this study really goes into, but students, the one that really was like a wow for me was 50% of the academic year gains that students made after 7th grade in math, half would be lost after the summer. That's incredible. That's like you're taking 2 steps forward and 1 step backward. So that's another, sort of like driving force behind this research that I did. And then finally, this is more verification of the POGIL strategy, process-oriented learning, being more effective than traditional lecture. And this was in a pharmaceutical sciences setting in a 2015 study. So again, the 3 main components are self-guided inquiry, preventing academic loss during extended learning breaks from learning during extended breaks, and then hands-on activities, right? So those are the 3 main things. All right, so let's look at the participants real quick in this study. This was two of my honors physics classes last year. This was conducted at Jack Singley Academy, where I work at now and where I worked at then. 21 male, 21 female, 42 total students, 29 Hispanic, 9 African American, 4 Asian. And these are from, again, two of my honors physics classes. Let's talk about the research methodology. How exactly did we perform this project? Okay. All right, in the research method portion, so the first thing that we're going to look at is exactly what TEKs were they studying. They were studying the law of conservation of energy in physics. And just a quick breakdown of that is that essentially the energy throughout an object's motion is conserved. So the motion, the energies, the total energy is always going to be the same within a closed system. And so you can use this to calculate different things. So for example, what they had to do was they had to measure the height of a swing, like how far up the swing was brought. And with that measurement, they could calculate the potential energy at the top of the swing and then also make a guess, a sort of calculated, sort of like a calculated guess as to how fast the object would be moving at the bottom of its motion at its fastest point, where all the potential energy is converted into kinetic energy. So essentially the students make one measurement, the height, and then they can predict the velocity of the object, okay? So that's sort of all their questions were based off of this particular calculation. So I gave a pretest to see if the students were able to do this just baseline. Then we did an in-class lab that essentially involved the use of pendulums to walk them through this. The students self-selected into control and experimental groups. The experimental group students performed a self-paced guided inquiry process activity over the Thanksgiving break last year. Those in the control group did not. That was the only difference. Everyone else received the same instruction. Everyone received the same instruction, the same labs, the same activity, the same preparation. More in-class practice after the Thanksgiving break, because obviously during the break, they're gonna forget a lot of the stuff we did before. And then a post-test to compare outcomes for, did the students who did this project actually perform better? And so the students were, they self-selected. I did not want to assign them into groups. So the students decided, we're gonna do this or we're not gonna do this. 23 were in the control group, 23 students out of the 42 said they just didn't do the project, and 19 decided that they wanted to do the project. And then some students created posters summarizing their results. Let's have a look at all this stuff in a little bit more detail. First, let's look at the data that we generated. The data shows the percentage of students who scored correctly on their pre-test and post-test. So here's the pre-test, here's the post-test. Orange bar represents the control group students. The yellow bar represents the experimental group students. The numbers, 13 and 11, represent percentage of students who answered the pre-test correctly. So 13% of the control group students answered the pre-test correctly. 11% of the experimental group students answered the pre-test correctly. And then in the post-test, 65% of the control group students answered their question correctly, and 79%, almost 80% of the experimental group students answered their question, their post-test question correctly. So before, there was a 2% difference and in the pre-test between the two groups, with the edge going towards the control group. And in the post-test, there was a 14% difference between the two groups, with the experimental group edging out the control group. Let's have a look at more of these results in a little bit more detail. So let's have a look at the results section of the poster. So for the results, the students could finally create a poster. This was optional and of course extra credit. This sort of summarized not only the science and the scientific method behind their experiment, but also the physics calculations involved and all the different ways that they could calculate, okay, how do we actually calculate the velocity of the object at the bottom of its swing? And so this particular student calculated a velocity of 1.73 meters per second based on their particular body weight and also how high up they brought the swing initially. And so they were given meter sticks. This was purchased with grant money that was provided by the WIPRO program. And the meter sticks were given out to the students. Both groups had similar performance rates in the pretest. Not a lot of the students did well in the pretest, 13%, 11% respectively for control and experimental. On the post-test, there was major improvement. Control group improved by 52%, experimental by 68%. The control group performed better in the pretest by 2%, but the experimental performed better than the control in the post-test by 14%. So this is, when I first got these results, I was like, yes, because, there's always that part of you that's like, oh my God, like what if like the control group students do better? I mean, I still have to present this research, but, obviously you want the results to look a certain way, and they actually did in this case. And I was extremely happy when I first like crunched these numbers. It was incredible. It was an incredible feeling. This must be the feeling that scientists feel when their hypothesis is corroborated through their research. So this was incredible for me personally. Let's have a look at let's discuss these results real quick and what these numbers actually mean. So we can conclude potentially that it's possible that the reason why the experimental group students did better than the control group students in the post-test was because they performed this activity. And that would be somewhat simplistic because there's other things to consider. Number one, well, we'll talk about that in the implications. Another thing is that both groups improved. Without question, both groups improved, and that was because they both received in-class instruction, in-class labs. I don't even go into all that pedagogy that I did in class. That's not the focus of this particular poster presentation. But the greater improvement in the experimental group could potentially be attributed to the fact that they participated in this self-paced guided inquiry learning over the Thanksgiving break. These pictures represent an app that I wanted to use. It's called Playground Physics. It's eponymous with this particular presentation. And here they could calculate the height of a swing, and then the program would generate the potential and kinetic energy based on these different parameters that they would also calculate using their handwritten, self-guided lab. And then they could use the app to corroborate their results. The original idea was to use this. I could not do this, and I'll explain that more in the implications section. All right. So for implications for future research, the students were self-selected. I did not want to say, no, you must do this project, and to half the students and tell the other half, no, you can't do this project. I didn't want to exercise that type of control over the students. So I told them, look, you guys decide whether you want to do the project or not. And that way, the ones who decided to do it, hopefully they would put their heart into it. And I think that's what happened here. So, and that's the thing. Because the students were self-selected, it's possible that perhaps those self-selected students were just more academically motivated. Perhaps they were A students, they scored better, they had easier time understanding concepts. And so because of that, that's why they improved more, not necessarily only because of this activity that they did over the break. So that's one of the caveats, one of the catches to this self-selection that the students did. So future studies have to ensure that the variable responsible for the differences that we observed in the results are actually due to this activity and not due to other variables that were not controlled in the experiment. So one thing that I could have done differently was to to allow the students to self-select just like I did, but then to also break down the groups by grade, like how well do they perform academically. That way I could see, okay, do the control students and the experimental students both have similar academic performance? Are there kind of an even distribution between, advanced A students, intermediate students, and then threshold performers? If both groups had the same sort of proportion of these three groups, then I could more easily say that the reason why the experimental group did better was because of this activity. I did not do that at the time. I thought about doing this. I didn't. My bad. If I could do it over again, I would. For future studies, you should. And then another thing would be to include the use of the app that could allow them to confirm their calculations through the use of an app. That would just be awesome. If you calculate something and then the app says that what you calculated is fairly close to, whatever the app is showing is close to whatever you calculated, that just feels good, and that's good for the students. But technical issues, the app was working well for me. When I was logged into the student Chromebooks, But when the students logged in, it didn't work for them. So I had to go through a whole thing with information technologies services through our school to unblock the playground physics app. By the time all this happened, the project was already going. So I just decided to nix that. If I were to do it again, I would anticipate this and do this way earlier. This whole unblocking of the technology, and then probably giving the students a lot more experience with the playground physics app before they go out into the field and like use this app on their own, because that's another major component, is teaching them that part. But at the end of the day, we still were able to combine hands-on activities, preventing learning losses over an extended break, and we were still able to address the whole self-paced, self-guided inquiry learning, POGO learning, as a means of improving learning outcomes between control and experimental groups of students. And so, yeah, despite these limitations, we were still able to, I say, accomplish a few successes. So for that, I'm very happy. And that's all I have. That's my presentation. I hope you all enjoyed it. I hope you guys have a blessed and wonderful rest of your day. Thank you so much. I really appreciate y'all. Take care.